Right, we're on aerobic respiration. So let's look at some time frames again. So we need the majority of stuff. So if we get a time frame up from 0 seconds to 3 hours, let's just run through quickly all of our energy systems. ATP splitting to initially release energy in order to cause muscular contractions and move. Once that's broken down, it needs to be resynthesized. So first of all, if we're sprinting for as fast as possible, we are going to use the ATP-PC system. Okay, that's going to be our fastest breakdown of energy in order to resynthesize ATP. That only lasts 8 seconds though, so after that, I'm then going to use my lactate anaerobic system. Remember, that can last up to 3 minutes, and then kind of anything after that is going to run into aerobic respiration. Now the majority was a little bit different because for 8 seconds, anything up to 15 seconds, okay, is where I would use my ATP-PC system for. Then anything up to 5 minutes and 59 seconds is going to be for my lactate anaerobic system. And then anything where a question asks about past that, again, is going to be aerobic respiration. Okay, fine. So we need to get into the process. The process is quite long. The easiest way for you to remember this is going to be through repetition. Okay, so first of all, we have the process of glycolysis. That is still a part of aerobic respiration. Okay, however, glycolysis is anaerobic. So we start at glycogen. That gets broken down into glucose. Glucose is broken down into pyruvate. Now, in the lactate anaerobic system, because there's not oxygen, all right, here it would convert to lactic acid, but this isn't the case here, all right, because there is oxygen now, which means that it is oxidized. What that means is for us is that it's exposed to oxygen. So as soon as pyruvate is oxidized, instead of lactic acid, I get this thing called acetyl-CoA. Acetyl-CoA is very, very important because it allows us to enter something called the Krebs cycle. Okay, without acetyl-CoA, you can't enter the Krebs cycle and you can't access aerobic respiration. Okay, so we're always going to try and get back to this acetyl-CoA. So, like I said, the acetyl-CoA, it enters the Krebs cycle, okay, and it converts it, right, into something called oxaloacetic acid. Let me just run back right to the beginning for you. So first of all, you've got the process of glycolysis. Glycogen is broken down into glucose. Glucose is broken down into pyruvate. Pyruvate is oxidized to form acetyl-CoA. That allows us to enter the Krebs cycle. The Krebs cycle converts acetyl-CoA into oxaloacetic acid. Now, that then in the muscle will combine with coenzyme A, and that forms something called citric acid. Okay, let's just go back to here then. So acetyl-CoA enters the Krebs cycle, which converts acetyl-CoA into oxaloacetic acid. That combines with coenzyme A to form citric acid. Now, from there, I also get a byproduct called hydrogen. Now, hydrogen is really important because it allows me to access something called the electron transport chain. Okay, so we're nearly at the end of this now. So hydrogen travels down the electron transport chain and I get two things. The first thing I'm going to get is water, H2O. But this is the important part now. I get 34 ATP. Now compare that to the phosphocreatine system. Each breakdown of phosphocreatine only resynthesizes 1 ATP. Glycolysis, here I got 2 ATP. Okay. However, the issue is that it built up lactic acid. Now here I'm getting 34 ATP. Okay, so I get a hell of a lot more energy. Now, once I've done this, I can also access my fat stores. So when we start thinking about lower intensity exercise, this is where we start associating fats with that kind of exercise. Okay, so fats can then be broken down, right? They're broken down, but you've got to remember, where are we trying to get back to? We're always trying to get back to this 34 ATP. Now, the only way I can do that is if I have acetyl-CoA entering the Krebs cycle. So that's where we're trying to get back to. So my fats or my triglyceride stores are broken down into fatty acids, which are then oxidized, okay, which we've seen up here where they're exposed to oxygen, which form then acetyl-CoA. That then can re-enter the Krebs cycle, convert it to oxaloacetic acid, combine with coenzyme A, form citric acid, have a byproduct of hydrogen, travel down the electron transport chain, and I get 34 ATP again. Now, when we're thinking the evaluation of this, yes, I get 34 ATP, which makes you think that you should be able to work at a higher intensity. However, look at how many processes there are. This process is a lot slower, which means that if there's not oxygen available, pyruvate would just not get oxidized. So because it takes so long, that means I have to have enough oxygen and by working at a low enough intensity to support it. Okay, so when we're going to, and then last of all, the process of fats being broken down and oxidized, that is known as beta oxidation. You also need to know that. Fine, so I've got a question here, right? At the Beijing Olympics, David Dow's won the silver medal in the swimming in a 10-kilometre marathon event in a time of 1 hour and 51 minutes and 53.1 seconds. Now, when we're looking at it, again, explain how the majority of energy is provided. Now, in his last sprint finish, he would still use phosphocreatine stores. However, we've got to think, has that provided the majority of the energy? It won't have done. Okay, it can only provide it for 8 seconds of this 1 hour and 51 minutes. So the time frame is really, really important. Then it's got this explain how. Explain how is like, what is the process? What has actually happened? Okay, so then we would have to explain all of that aerobic respiration through the entire process and know it off by heart. Then, last of all, it was that majority word. Yeah, all three energy systems will have contributed in this time, but the majority would have been provided by aerobic respiration. So despite it being pretty long, you would still have to write that entire process that we've just been through. Then we have the evaluation of it. So the advantages of we clearly saw that when I break down fats, okay, when I break down fats, I end up with 34 ATP. Let's compare that to carbohydrates. When I break down carbohydrates, I only get 2 ATP. Okay, now let's say that's per gram. So per gram of fat, let's say we got 34 ATP back. Well, I only got 2 ATP back from breaking down glycogen into glucose into pyruvate. So these fats yield more energy per gram than carbohydrates. And that allows 34 ATP to be produced. Then aerobic respiration also allows the performer to oxidize lactic acid. So when I'm running during a race, let's say there's a period in a marathon and I decide to work at a higher intensity, that might mean that I start to produce some lactic acid. However, when I go back to accessing aerobic respiration again at a lower intensity, that would then mean that some of that lactic acid can be oxidized whilst I'm still working. You don't necessarily have to stop whatsoever. Okay, think about it in a game. You're always moving around in a game sport. However, I can still build lactic acid and remove it throughout the game, and that's how aerobic respiration is beneficial to use in, especially in game sports and marathons. However, the energy release is slower than the lactate anaerobic system and ATP-PC system. It's really slow compared to them. So whereas I get 34 ATP, it's so slow. Okay, like we say, it takes 3 minutes to even access it during exercise, right? And also because of all those processes that take place to get to that 34 ATP takes longer than me just going breakdown of a PC or break down the glycogen, break down the glucose. Okay, which means that I will have to, or as we just said, we can't regenerate ATP as quickly. If I can't regenerate ATP quick, that means I then have to work at a lower intensity. I want you to think about it. Who are the best athletes? The best athletes are the ones that can use aerobic respiration at the highest intensity. If I've got two performers, a trained athlete running at 12 miles an hour, and they're using aerobic respiration, they're not building up lactic acid. Okay, it means they can hold that pace for kind of as long as they want to. Whereas me, if I was to run at 12 miles an hour for probably 1 minute, is I would be building up lactic acid because I am not as good at utilising this oxygen. Okay, so it would have to be used at lower intensities. Usain Bolt can't use aerobic respiration during a 100 metre sprint. And that kind of concludes it all. Because I can only use it when there's enough oxygen present. That enough is kind of a key word there. If you don't talk about enough, right, then